So tonight we're going to talk a little bit about optimization. This is really just finding the maximum or minimum of a function. Some of the problems will ask you for that y value, the max or min of the function. Some of them will ask you for information that depends on you finding a max or min, and we'll see some examples at the end of this lesson. So when you're doing these problems, one of the important pieces is to actually show that you found a max or show that you found a min, not just that you found a critical point. AP graders will be looking to see what calculus you use to make that determination. I have seen some AP grading rubrics that say must use first derivative test or second derivative test. I have seen other AP grading rubrics that actually allow you to just say, oh, it was a parabola and I know it was face up because the leading coefficient was positive. But I want you to get in the habit of just using calculus to prove this. There are lots of ways to rationalize or use logic to say, well, the point I found has to be a maximum or minimum, but I really want you to make sure you use calculus so that the AP graders have no reason to disbelieve you. Does that make sense? All right, so just a quick review. If you have a critical point, that's where your derivative equals 0 or is undefined. And what you want to test is, for first derivative, if the first derivative is less than 0 for all the x values that are before that specific c value, that x that you found where your derivative is 0, and your first derivative is greater than 0 for all the x values that are greater than c. So what this means is your first derivative is negative before the critical point, your first derivative is positive after the critical point. That means you're going to have what kind of critical point? No, really answer. Hopefully you all said minimum, because this means that your function is decreasing and then increasing. So that means you have to have a minimum. On the flip side, and of course you can all guess the answer to this one without having to work for it, because this is the other critical point. If your derivative is positive before the critical point and negative after the critical point, that means your function is increasing before the critical point and decreasing after, so therefore you have a, that's right, maximum. You can also do this with a second derivative test. If the second derivative at your critical point, that c value right there, if your second derivative at that critical point is less than 0, that means you have a, again, really answer, minimum. Good. And if your second derivative is greater than 0 at that specific x value where your critical point was, you have a minimum. Just a reminder, we've done this before, but you need to use these when proving whether you have a max or a min of these particular word problems. They're a little bit like related rates, not a whole lot, but a little bit. There are some features that are going to be important to do, or steps that it will be important to do for this problem, just like there were steps that were critical to do before for related rates. So here's an example. A farmer has 2,400 fet. No, that should say feet. Sorry about that. Of fencing, okay, and he wants to make a fenced off area of his field. The field borders a river. The river is straight, and he does want to make a rectangle. What are the dimensions of the field that has the largest area? I'm guessing some of you are already thinking, well, duh, it's going to be a square. I just have to figure out what square side lengths would make 2,400 feet of perimeter. Yes, that's true. I don't want you to try to rationalize these out. I want you to actually use the calculus. So we know what to expect. We expect a square, but let's prove it using calculus. This is how you're going to get full credit on your AP. So sketch and label a diagram. Set up one or more equations using the given information. And remember, this is often easier to do if you only have 2 variables, not 3. So here's my diagram. I have the perimeter here. I have an equation for perimeter based on my labels of my diagram. And I have an equation for area, again, based on my labels for diagram, and I substituted in for y here. Multiplied it out, found its derivative, found where the derivative is 0, because that's going to give me a critical point. That critical point happens when x is 800. Solving for y using the perimeter equation, I get that y is also 800. I do, however, have to show that this is a maximum area. Okay? I chose to take the second derivative of area, and I found that my second derivative is -4 Therefore, since my second derivative is negative, I have something that is concave down, and therefore I have a maximum area. So you do need to say all these things as well on your exam, not just show these things, but you need to say something like, okay, a double prime is less than 0 at my critical point, x equals 800, therefore it is a maximum. Does that make sense? Okay. I have a couple of problems for you to try on your own. I do want you to really do these on your own, but then check to see what you get for solutions if they match what I did. Find the point on the parabola, y squared, be careful, y squared equals 2x, that has that is closest to the point 1,4. So a point on this parabola that's closest to this point. A picture, one or more equations, and again, use those two equations to make sure you only have one equation that that you have two variables for. Okay, so set it up, try to solve. We're trying to minimize because we want closest. Oops, sorry. Give it a try and then check back. Press pause. So what I did is got myself a little diagram by graphing. I used GeoGebra to graph. And then I used some equations. Here's my original equation for the parabola here. And r squared is going to be the distance between point A and some random point on, well actually r is the distance, between some point on my parabola and A. I used r squared though because having a square root here makes things really messy and really challenging to take derivatives. So I just said, well, if I want r to be smallest, I also want r squared to be smallest. So I left my function as r squared. I wanted to put it in terms of one variable, so I replaced x using the original equation for the parabola, and I came up with this lovely little expression. I took the derivative of that, and I used power rule and chain rule to get this expression, and then simplified it a little bit. So I just put stuff together, and this actually simplifies down really nicely to y cubed minus 8, because I end up with a negative 2y here, and I'm adding it to 2y, so those go away. So I just end up with the y cubed and a negative 8. I want to know a critical point, so I'm looking for where that function is equal to 0. Solve and we get y is 2. I need to know that this actually is a maximum, sorry, not maximum, a minimum. So I took the second derivative of my function. So here's my first derivative right here. And I took the second derivative. My second derivative is always, 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 always positive. So I know I have a minimum. I just showed that, in fact, my second derivative is positive when x equals 2, instead of leaving it up to chance. Now that I know that, I know I have a minimum distance, but oh, we are not done yet. We still have to find the point. Remember, we were requested to find a point on the parabola. If x is 2, I plugged, y was 2. So I plugged 2 into the original equation for the parabola for y, and got that x is also 2. So the point is 2, 2, and that is the closest. Again, you are going to have to be explicit for the AP graders and say, hey, this derivative being greater than 0 means I have concave up, which means I have a minimum at my critical point. You're going to have to express all that a little bit in words, a little bit in math notation. Got it? Excellent. Moving on. I have two problems here for you to do on your own. So I've given you two examples, and I want you to try these two on your own and come into class being ready to discuss them and present them and share where you got stuck and where you found success. So I have a couple of little hints for you here. For the cylindrical can, you just need to remember volume and surface area. The cost of metal is going to throw you off a little bit, but cost of metal to manufacture the can means that we're talking about how much metal. So if we're minimizing cost, we've got to minimize the metal, and that means surface area. So we are dealing with volume. They've given us information about that, but they're asking me to minimize surface area. So I've given you over here, hidden behind the wall, some equations that'll help you out. A man launches his boat from point A on the bank. This thing is ridiculous to read. Read it through, see if you can make sense of it. And then I have a picture that will really help. Okay, and we'll talk more about how to make those pictures on your own. But the goal is to get this guy across a 3-kilometer wide river that runs up and down, runs north-south, and he can both row and run. So he's going to row across the river, but then run part of the way. Okay, so there are 2 rates going on here that you will need, and the reason you need those is because we want to know how much does he run, how much does he row in order to get there fastest, as quickly as possible. So that's talking about time. Okay, so where should he land the boat? So we want to know where on the opposite shore over here should he land the boat in order to get there fastest. So take a couple minutes to think about these. I'll show you the hints. You can press pause if you want to work without a hint in a minute. So here's the hint for the cylinder, volume and surface area here, 2 formulas you will need. And here's the hint for the boat. So the river's 3 kilometers wide. He's going to go across at some point and run, but we don't know if he's going to go straight across and run or if he's going to go straight to point B in his boat and not run at all, or if he's going to land somewhere else on the side of the river and then run a little bit. From A to B, that vertical distance is 8 kilometers total. River, 3 kilometers wide. I labeled an X here, which should be handy in helping you figure out this distance here. And you should be able to come up with an expression for this distance here. Okay? So you have distances. Remember, we are curious about time, not distance. So we want some equations for time. See you in class. Good luck.